Black holes are among the most enigmatic objects in the universe. They captivate scientists and enthusiasts alike with their mysterious nature and immense power. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This makes them invisible to the naked eye, detectable only through their interaction with surrounding matter. Imagine a place where the fabric of space and time is warped beyond recognition. This warping can bend light and distort the view of objects behind them, a phenomenon known as gravitational lensing. These celestial objects are born from the death throes of massive stars. When these stars exhaust their nuclear fuel, they undergo dramatic changes. When a star much larger than our Sun runs out of fuel, it can no longer support itself against its own gravity. The outer layers are expelled and the core begins to collapse. The core collapses in on itself, creating a singularity, a point of infinite density. This singularity is the heart of the black hole. This collapse is so violent that it sends shockwaves through the star, ripping it apart in a spectacular explosion known as a supernova. The energy released is immense. The remnants of this catastrophic event form a black hole. The material that doesn't escape is pulled into the singularity. These cosmic abysses are not empty spaces. They are objects of immense mass concentrated into an incredibly small volume. This makes them some of the densest objects in the universe. This extreme density gives black holes their defining characteristic, their gravitational pull. It is so strong that it can affect the orbits of nearby stars and even bend light. Surrounding a black hole is an invisible boundary called the event horizon. This boundary marks the limits of the black hole's influence. This boundary is not a physical barrier, but rather a point of no return. It is the threshold beyond which nothing can escape. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. This includes stars, planets, and even entire galaxies. Not even light, the fastest thing in the universe, can outrun a black hole's grasp from within the event horizon. The immense gravity bends light around it. Imagine you are approaching a black hole in a spaceship. The closer you get, the more intense the gravitational pull becomes. As you get closer, you would notice that time seems to slow down for you relative to someone observing from a safe distance. This phenomenon is known as time dilation. This is a consequence of Einstein's theory of general relativity, which states that gravity warps time. The stronger the gravitational field, the more time is distorted. At the event horizon, time would appear to stand still from the perspective of an outside observer. This creates a fascinating and eerie visual effect. You would be forever frozen on the verge of disappearing into the black hole. To an outside observer, you would seem to hover at the edge indefinitely. However, from your perspective inside the spaceship, you would continue to fall inward, eventually reaching the singularity at the center of the black hole. This journey would be one way with no possibility of return. For decades, scientists believed that black holes were completely black, swallowing everything that came near them. However, in 1974, physicist Stephen Hawking made a groundbreaking discovery that changed our understanding of these enigmatic objects. Hawking showed that black holes are not entirely black after all. He proposed that they emit a faint radiation, now known as Hawking radiation, due to quantum mechanical effects near the event horizon. Quantum mechanics is the branch of physics that governs the behavior of particles at the atomic and subatomic levels. According to quantum theory, empty space is not truly empty. Instead, it is teeming with virtual particles, constantly popping in and out of existence. Hawking realized that if a pair of virtual particles were to appear near the event horizon of a black hole, one particle could fall into the black hole, while the other escapes into space. Hawking's discovery of black hole radiation led to a profound puzzle known as the black hole information paradox. The paradox arises from the conflict between quantum mechanics, which suggests that information cannot be destroyed, and general relativity, which governs the behavior of black holes. According to quantum mechanics, information about the state of a system is always conserved. This means that if you know the initial state of a system, you can, in principle, determine its final state, no matter what interactions or transformations it undergoes. However, Hawking radiation seems to violate this principle. The radiation emitted by a black hole appears to be completely random and carries no information about the objects that fell into it. This suggests that as a black hole evaporates through Hawking radiation, it gradually erases all information about its past. violating the principle of information conservation. Why is the information paradox so significant? Information is not just an abstract concept in physics, it is deeply intertwined with our understanding of the universe and its fundamental laws. In fact, some physicists believe that information is even more fundamental than matter and energy. Imagine you have a book. The information contained in the book is not about the physical paper and ink, but rather the arrangement of those materials. You can burn the book, but the information it contained, the stories, the characters, the ideas, is not necessarily destroyed. Similarly, in physics, information refers to the specific arrangement of particles that make up an object or a system. This information determines the object's properties and behavior. If information were truly lost in a black hole, it would have profound implications for our understanding of the universe. The black hole information paradox has puzzled physicists for decades, leading to numerous attempts to resolve it. This paradox arises from the conflict between general relativity and quantum mechanics. Some physicists believe that information is indeed lost in a black hole, which would require a fundamental revision of quantum mechanics. This idea, if true, would have profound implications for our understanding of the universe. However, this idea is highly controversial and challenges our current understanding of physics. It raises questions about the very nature of reality and the laws that govern it. Other physicists propose that the information is not lost, but rather encoded in subtle correlations within the Hawking radiation. This theory suggests a more intricate structure to the radiation emitted by black holes. This idea suggests that while the radiation appears random at first glance, a closer examination would reveal hidden patterns containing the lost information. These patterns could hold the key to resolving the paradox. Another possibility is that the information is not lost, but rather transferred to another universe or dimension. This concept opens up fascinating possibilities about the nature of our cosmos. This idea stems from theories that suggest our universe is not the only one, but rather part of a larger multiverse. Each universe could have its own set of physical laws and constants. In this scenario, the information falling into a black hole could emerge in another universe, preserving the principle of information conservation. This would mean that information is never truly lost, just relocated. One of the most intriguing and radical proposals for resolving the information paradox is the holographic principle. This principle, first proposed by physicist Gerard T. Hooft, suggests that our three-dimensional universe is a holographic projection of information encoded on a distant two-dimensional surface. Imagine a hologram. It is a two-dimensional object that can create the illusion of a three-dimensional image when illuminated correctly. Similarly, the holographic principle proposes that the information content of our universe is encoded on a distant boundary like a cosmic horizon. This principle has profound implications for our understanding of reality, suggesting that our perception of space and time might be an illusion. While the holographic principle is still highly speculative, it offers a tantalizing glimpse into the potential unification of quantum mechanics and general relativity. The black hole information paradox remains one of the most challenging and fascinating puzzles in modern physics. Scientists continue to grapple with the implications of Hawking radiation and the fate of information that falls into a black hole. The search for a solution has spurred new theoretical frameworks and experimental endeavors, pushing the boundaries of our understanding of the universe. Some researchers are exploring the possibility of simulating black holes in laboratories using ultra-cold atoms, hoping to gain insights into their behavior and the information paradox. Others are looking to astronomical observations of black holes and their surroundings for clues. The Event Horizon Telescope, which captured the first ever image of a black hole's shadow, is expected to provide valuable data that could shed light on the information paradox. The black hole information paradox is a testament to the power of human curiosity and our relentless pursuit of knowledge. It highlights the profound mysteries that still lie at the heart of our universe, waiting to be unraveled. While the paradox remains unsolved, it has spurred some of the most exciting and innovative research in physics. The quest to understand black holes and the fate of information has led to new theoretical frameworks and experimental techniques, pushing the boundaries of our understanding of the cosmos. The allure of the unknown continues to drive scientists to explore the universe's deepest secrets, and the black hole information paradox serves as a constant reminder of the vastness of our ignorance and the infinite possibilities that lie ahead in our quest to comprehend the cosmos.